Okay. Well, I'll begin. What do you see happening in terms of the timeline of the project over the summer?
Well, we've got a presentation coming up. The main goal right now is to resolve our current. So the current status of the project is that we have the pressure pot drilled out for all the heater coils going in and the pressure solenoid coming out. Hardhik has shipped a control board for us to integrate into the system. I should be receiving that probably next week, most likely, or maybe this weekend. And there's a couple of issues that we have with the new coil that we've got designed for this application. I can actually jump over to better pictures, because that was an issue.
So, yeah.
Can you see my screen still?
Yes, we can see it.
Okay, you can see the photo library.
Yes, we can.
Okay, yeah. So like this is like an example. So this is so this was original. This is one of our original prototypes, but this one uses a smaller that cup's the size of maybe like a small water cup. It's very small. And our new version is much larger. So it's basically like flower pot sized. And so what we're doing with right now is trying to get the making sure the coil is able to handle the flower or the pot size that we have currently. So all that's been done. Right now, we resolved an issue with how to connect the larger coil with the higher power supply.
Mm-hmm.
So previously we had it hooked in with this wire system here, and that was I had about a 1 ohm resistance with the plug, and the cable size was too small. And so what would happen is that I wasn't getting induction happening inside the coil. Also, the coil itself was loosely coupled. And so you can see it here. The distance between the coil to the windings was too wide. And so we're doing two things. We're compressing the coil, and we're making a direct connection between the copper coil and the induction heater, or the induction power supply.
Yeah. Well, so I'm sure you'll get that worked out. The milestone that I'm looking for is being able to do induction inside a sealed pressure chamber, right?
Yes.
I mean, that will be the big step. Whether the cup that can hold the sample is as large as the one you're trying to do or not.
So we've fabricated these pass-through couplings. These use a PTFE insulator, and so the copper tubing passes through the insulator, and the insulator prevents contact between the aluminum enclosure and the copper coil. And that's our plan for basically how to basically keep this thing pressure tight for about 15 psi without leaking.
Okay, good. So, I mean, hopefully, let's say by August, we'll be doing induction, which produces char inside a sealed vessel. We'll be driving off the water by vaporizing it, flashing it off with a solenoid, and then eventually removing all of the water and beginning a charring phase where the temperature rises beyond the vapor temperature water, and you start to carbonize the material.
Yeah.
Okay.
We've done all that separately. What we're doing now, hopefully what we're doing is we're going to combine all that together so that we can basically present it as a fully unified system.
I see. Okay. And since I created this project, I should know, but you guys haven't found anyone who's doing the combination of charring with induction in the samples, right? This is innovative in that sense. It's that no one else is doing that at all, right?
I mean, as far as I know, like I mean, this is a weird mix of material properties that I don't think people are looking at currently. But even if they are, they're not doing it in open source fashion like this. So
okay,
no, I don't think there's anybody doing an open source induction toilet system using kitty litter and magnetite.
Okay, and then so what is your expected procedure for removing the biochar from the kitty litter? Is it, you know, something that someone can just do like with a metal scoop, or do you have to sieve it, or what?
So that's still, and I think Peter might have some more content on this one, but right now what we're looking at is that there's a couple of, we need we're going to basically add in some capacity, a agitator. And the agitator itself may also double as a sifter. So we're not entirely sure if we're going to basically like shake it or stir it or mix it or vibrate it. But what we're going to do, what we're basically doing, what we're going to basically end up doing is we're going to need to have some method of both mixing up the kitty litter so that it makes as much contact as possible. And then also that same process should also double as a way of decarbonizing the material. And then that's what we're going to basically use for pulling it out. There may be a method. I mean, we may have a process where we have to like pull out the. We may have to sift out the kitty litter and then be left with like a bucket full of like char or biochar. But I don't think we've got a really good idea like what that'll look like yet.
Yeah, best case scenario, one of the solutions that we were talking about is making our own magnetite doped bentonite clay, like balls or spheres. And once creating the biochar, ideally we'll have a series of mesh filters, like a high temperature sack, and be able to just take it out and give it a good shake to pass the ash through the filter, and then the liner that we'll be shaking will be full of the bentonite, magnetite, clay particles, and we'd be able to just put it back in the vessel.
Okay, so I mean, basically, sieving it is a baseline way of separating it, right? Mm-hmm. You use it a certain number of times until biochar is being built up, and you're like, okay, we need to remove the biochar. I mean, in the worst case, you just put a scoop inside there, you know, and you scoop it all out, leaving the biochar in the chamber, and then you take the biochar out and put the kitty litter back in the chamber.
Right.
Yeah.
Most ideally, we'll figure out a more automatic method.
Sure.
A little more hands-free.
Sure. Yeah. Well, I mean, that can always be done. I mean, you know, if we can just get this all done under pressure, then we can move on to the next phase of the project, I think.
Yeah. If we get this problem solved with the larger vessel, the next part is just integrating it into the pot. Worst case scenario is we drill a third hole and we set up our smaller system inside the pressure pot, and then we just get a plug for the unused hole in the side of the pot.
Okay. Do we have any questions from anyone else in the audience?
What's happening right now is that this was one of our experiments that used pure magnetite and just water mixed in. And we're basically showcasing that the water is basically being boiled off rapidly as we speak.
Mhm. Well, from a development point of view, go ahead, Megan.
Sorry, I was just going to ask, could you go over, I might have missed it, but if I didn't, could you go over the relative cost if someone tried to reproduce the system? I know you might not have a release bomb right now, but for those who might want to iterate or fork your project on GitHub.
Right now, the biggest cost is going to be the power supply. The inductive coil and the heater itself are like, I think, under $100. The power supply is, I think, a $300 power supply. The pressure pot is maybe $100, $150 max. The fittings and the couplings and all that are probably the other biggest cost, because we're basically having to modify and make those fit. So the biggest cost long term is going to be the power supply that will provide the peak power for running the system. After that, like when we can like get like bulk pricing on the fittings and all that, then most of those costs will all go down to something pretty reasonable.
Yeah, the solenoid valve is also fairly expensive because it has to survive high pressure and steam temperatures.
Yeah.
Right. So.
No, what I wanted to ask is sort of following up on what you asked in the middle of the presentation, why not incinerate? I think I understand why not incinerate, but if you could compare the cost difference of operation between an incineration approach versus the biochar approach, I'm interested to know like how that affects the operational cost.
You're still muted, Lawrence.
The biggest one is going to be basically the duration and the temperatures having. So both of them have to reach high temperature. The incineration toilet has to reach a higher temperature. And it also, if there is water in the system, it also doesn't have a method of easy energy transfer. So an incineration toilet normally is it's like when you take a like an electric like pot and you try to heat it up and you try to like boil off all the water inside the pot. It takes a long time and a lot of energy. The induction has two major advantages. Even on a stovetop, the induction heater directly heats the material. So you're not making contact from a heating element and then touching on heating up your pot. You're directly heating the material that's making contact with your sample. And on top of that, our particular system has a large amount of surface area so that we can basically evenly heat at the same time the entire sample. And we also don't have to have the full volume of the chamber hot to be able to reach the temperatures that we need to dewater and then pyrolyze the material. So an incineration toilet has to reach the entire vessel has to reach an operating temperature to operate, which means that the entire volume has to be at the same temperature. Our system, only the material that's encompassed inside the magnetite envelope, which is technically insulated by the bentonite or calcaline clay material or kitty litter. It basically creates like a envelope that both acts as like an insulator, but it also acts as a heat susceptor. So we basically get direct heating of the material, as well as it helps keep the heat centered on the device itself. It's not really obvious.
It sounds like you're espousing the benefits of induction versus resistive heating, as opposed to biochar versus incineration.
Well, yes. Both systems would. Our system could basically do both. If we incinerated the sample, the main difference would be that we would leave the top off. We'd add oxygen into the environment. So from an energy standpoint, actually, maybe Robert knows this. Is there like an energy difference between pyrolysis versus burning?
Combustion, yeah, right. Well, so yeah, I mean, let me take a step back here, okay? So this system is probably going to have higher capital cost for the electrical system, okay? And what we haven't talked about is the gas processing, which goes after you flash the gases off, because you still have to do something with them, okay? Because they're going to smell bad. Okay. Now, what do you do with those gases? I assume in incineration toilets, they simply use a fan and what we would call like a stovepipe, and they drive the exhaust gases relatively far away from the domicile. Okay. Now, that is a significant cost in the sense that you have to install it, and it's a mechanical part that, you know, can break down. We also have that problem. Now, my hope is as a separate modular thing, because as you know, I want everything to be open source and everything to be researchable in a separate system, is that we will somehow chemically treat the off-gas material in order to decrease the odor, which is really the main problem. But you also have to recover the water, okay? I mean, you don't have to. You can just run it out your window, but there is water in the sense of water vapor, and it's going to turn into water somewhere when it's released. So like an air conditioner, it's got to have a drain line of some kind. Okay, so we haven't really discussed that. Okay, now it's arguable that the electrical cost of this system will be a little lower than the electrical cost of an incineration system. Under most circumstances, fecal matter does not have a very high heating energy. Of course, famously, yak droppings can be used in certain environments as a fuel, but that is an animal that is an herbivorous brute, which a fair amount of material is retained in their droppings, which has a heating material. So I don't believe the combustion which occurs in an incinerating toilet is really self-sustaining. So you have to add a lot of heat to it to make it happen. But the energy balance is probably not the biggest expense compared to the cost of the ventilation that both systems have to have, right, and the capital cost. Okay, I don't know if Joe's satisfied with that. I'd like to mention something. I have studied a lot of videos that talk about something that makes me kind of nervous because it's expressed in such glowing terms that I'm not sure I really believe it. But people say that biochar really makes an excellent garden amendment because of the ability of the root hairs of plants to bind to the biochar on its large surface area and have both ion exchange and moisture exchange in that environment. I believe it, but I haven't done it in my own garden, so I don't know for sure that that's really true, but I suspect that that is true. Now, in a way, this sequesters carbon, but of course, the amount of carbon sequestered is very low compared to the amount of fossil fuels that Americans spend in their cars, for example. And so there's really not a lot of value in this in terms of sequestering carbon. But in terms of being a valuable garden amendment, this is actually a pretty serious thing. And if anyone's interested, you can look up on YouTube. There's a Spanish word, I think it's called terra preta, describing how this was used by the indigenous civilization in Brazil, which unfortunately has largely disappeared, but left behind enough pottery remnants that we know that they mixed fecal matter with charcoal and used it directly as a garden amendment. And you can find people saying that this has magical properties in the soil, which I'm a little skeptical of. But we know that ion exchange and humus are necessary for garden amendments under normal circumstances, and that's what compost is. And so it's entirely plausible to me that would be reasonable. Okay, if there are no questions from the audience, then I'd like to thank Lawrence and Peter and Hardhik for this work. I'd like to point out how difficult it is to do this kind of experimental work. It's a lot easier to just, build a circuit board or to talk about something theoretically and not build it. And what they're doing is kind of a messy, hands-on, innovative thing which has never been done before. And that, it's a lot easier to talk about it than it is to actually do it. So they didn't show you the toast they made or the carbonized cheese puff they had. But it's pretty impressive, the work that they're going to do. So I think that we can keep, if the team keeps going a year from now, I think we're going to have something significant.
I'd like to hear from Peter and Hardhik and Lawrence, what inspired each of you, like if you could just, in your own words, what inspired you to work on this project and what drives you about this project? What's the inspiration for you?
So this one's kind of interesting. I think I've got a lot of cats. So the idea of having a incineration toilet or a pyrolyzation toilet that I might use for cats is attractive. And I think Peter, when I started talking, I got Peter dragged into this, and I originally Peter was talking about like soil or like septic systems. I'll let him tell the story, but he was talking about wanting to do it for
like homesteading. Yeah.
So go ahead.
Yeah,
go ahead.
I got basically like I wish I could have a big story talking about how I'm inspired I was about joining this, but mostly it's Lawrence dragged me into this, and it was a good opportunity to learn practically how to do research and development of hardware. And so that's something I'm really interested in doing. As far as some personal benefit from this project, I'm interested in homesteading, being able to live off the grid and self-sustainable as much as possible. And so the idea of having a plug-and-play system for handling human waste and then converting that into a usable substance for like the gardening that I intend to do as well was pretty alluring. Saving lots of money on like the digging and setup of human waste infrastructure like septic tanks or getting hooked up to a city system whenever you're just on a bare plot of land is expensive. And so being able to just set something down and use it and gain something beneficial from it in return is pretty nice.
Hardhik, what about you?
For me, it would be the primary thing is the innovative aspect. It's like, I know it's a pretty like vague theoretical concept, but pulling it and getting it back, like getting it to work is something which excites me. And that kind of projects is what I like to work on. And then the second would probably be the humanitarian aid. Like once this work out, I think it would solve a lot of like sanitation problem right now. And there are like few parts in the world where there is like not a decent toilet, and getting a decent toilet is itself like a big task. And I would like to see like this one be like be able to tackle that problem over there, and keeping it open source would always definitely help out in terms of like humanitarian. So those both things, I think those both are the driving factors for me on the project.
Awesome. Thank you. Sounds great. It's also inspiring to me, but I'm glad you guys are actually boots on the ground doing it.
Yeah. I mean, the toughest part would be like basically like as Robert mentioned, we have like theoretically this would work, theoretically it does work. Putting all the subsystem together and making it to work is the biggest task for this project.
Yeah, the further we go along, the more variables there are to account for and more rooms for error. Yeah.
You know, I've always been inspired by something Buckminster Fuller said, that pollution is really a resource in the wrong place. You know, I mean, you know, we are talking about poop, so we're talking about an offensive, you know, material, but it's valuable when it's in the right place, right? And like when it's in the right place is sterilized and safely buried in your garden, then it's very valuable. And you know, people drive to the gardening store and buy cow manure, you know, and composted cow manure and sheep manure and so forth, you know, specifically to put on their garden, right? And yet what we do in the American sewage system, you know, is we take something which is valuable, not super valuable, it's not worth its weight in copper or anything, but it's a little bit valuable, and we flush it down the toilet using valuable water to carry it away and concentrate it in a place where it will be even more dangerous and more offensive if it were to leak into the water system. And then we treat it at that place, sometimes maybe getting some valuable byproduct from it, but maybe not. And it just seems like a very inelegant approach to solving the problem. You know, on a larger scale, one thing that Public Invention believes, even though I admit to being rather weak on chemistry, I don't consider myself a good chemist, is that in the future, we're going to have lots of suitcase-sized chemical plants you know, around our homes doing things for us that we don't have now, because the instrumentation for those things has become very inexpensive. Okay, and this is, you know, a kind of a chemical mechanical process. This is an example of it, right? And so instead of having a giant thing like a sewage treatment facility for an entire city, you know, we can do it on a point basis. Now, this does have some problems, right? Like if you have a suitcase size chemical factory, so to speak, that, you know, you've got to deal with the problems of the chemistry, the dangerousness of that on a small scale, but they're still all there. And so it requires a great deal of kind of intelligence to make a small scale chemical process like this. But that intelligence is exactly what is available to us now, you know, in terms of sensors, 3D printing, you know, all the kinds of things necessary to shrink these. And this one, you know, along with cooking, are perhaps the two most fundamental chemical processes, you know, which we need to have.
Hey, Rob?
You know, yeah.
I got a quick question for you. There's a video on YouTube about Fresnel lenses, and I had thought about using this in conjunction with, you know, distilling water as well as, you know, sterilizing effluent. Would it be okay if I posted that in the chat?
Sure.
Okay.
Sure.
It's probably 7 minutes. I don't want people to stop reading it, but I think you said we might be winding down, so I just wanted to.
Yeah. Yeah, you know, of course, I view one of the things of design principle I use that's really important, right, is the modularization of things. So a Fresnel lens can be used to provide heat into the system. So can the induction coil. So the power of the system should, you know, in a way be separated from other aspects of the system, such as the pressure management system. And then, of course, one thing that, you know, could be a problem here is the gas management, the gas treatment that comes out also has to be separated. Okay. Now, in the case of the induction coil, the power has to be very much integrated inside the pressure chamber, and that's the whole point, right? But the more we modularize things, the more it might be possible to use some kind of solar power for this, whether it's something magnified directly with a Fresnel lens, or as Lawrence and his team suggested, using photovoltaics fed into a battery.
Yeah, I'm actually thinking there's probably opportunities for hybrid systems that utilize both at different environments. There's a lot of times where raising the heat makes the catalyst function better, but ultimately may need a little electricity to create the final loop. But you don't have to use electricity for heat purposes, that kind of thing.
Yeah, the biggest problem with the Fresnel lens and things like that is that it creates a envelope on the outside where it gets hot, but it's hard for that heat to get into the sample directly, and so you get the same effect. Like you can always add more heat to it, and eventually it'll transfer into the entire sample. But the reason why induction is that it allows you to basically rapidly heat the sample all at the same time, with an even heating system, and also in a controlled environment, so you can verify that the sample is sterilized because it's at a high pressure, because it's reached a certain temperature. You have a high confidence level that's been sterilized. So like being able to guarantee sterilization, and that you didn't create this insulated puddle that maybe you got half of it but not the whole thing. Is one of the reasons why we've got a system like this. That's the other reason why we've also seen some other systems where they use steam generation to basically do similar systems, or like a thermal battery to kind of do the same thing. Because it doesn't actually take that much heat to do pyrolysis. You can actually do pyrolysis over a longer time scale at a lower temperature. But
let me comment on something that RD said there. Suppose you built a hybrid system. Well, what you would need to make sure it works is the same kind of electronic control that we were just talking about, right? Like for example, suppose you used a Fresnel lens to provide this heat. That might work great during a certain part of the day, right? And you could make a hybrid system that was like, well, okay, at this time of the day, the lens is doing everything it needs. We've got enough power. We've accomplished the mission. And at other times, it's not. We need to build intelligent systems to make that more robust, right? But that is exactly what we're talking about doing here. I mean, that is now possible because we have microcontrollers and more complicated systems. So I kind of suspect that kind of direct use of solar power will become more possible in the presence of more electronic intelligence, which is capable of using it.
It seems a lot more useful to use PV cells to charge the battery pack and then run the induction than try and, use a lens.
Yeah. It probably is as a baseline, right? Okay, but a Fresnel lens would be cheaper and it might provide enough power. Obviously, it doesn't provide this energy storage at all, right? So it becomes a problem of management, right? Now, when we talked about compost toilets, we said compost toilets are a problem because they require careful management, which I believe because I've seen them in use. They work great under ideal circumstances, but it's hard to maintain ideal circumstances. So
sure,
maybe
so
the
actually,
same thing could be used there.
That's a pretty a good segue. There's a post on LinkedIn somebody mentioned that the pyrolysis, I'll quote them, the pyrolysis angle is clever, but does the biochar output justify complexity? Simpler composting might already solve the core problem in the environments without the added infrastructure. So maybe you can just go a little more in depth into, you know, how you have to be so careful or how you have to have the ideal conditions for the compost to work.
So my experience using a compost toilet was this. Okay, if you, I used one. It was just a large box. It was a 2-chamber design. So you use one for several months, and then you close it, and you use the other. And the one that you're not using, the biological process composts for a certain period of time, and then you open it and take it out, and it's mostly, it's not sanitized because it's, of course, a biological process, but it's pretty effective. If you put the right amount of grass clippings on your waste, it actually doesn't smell, and it works really well. Okay. The problem is if you do something like have a party and a bunch of people come over to your house and an excessive amount of urine gets in the toilet, it can kill the bacteria that's in there, and the water changes things. So instead of aerobically processing, it starts to process anaerobically, and then it smells really bad. And it's really hard to recover from that. Like it's not obvious what to do. I mean, you should essentially, you can always add more grass clippings. That's effective, but it doesn't always completely solve the problem. Okay, so whoever said that on LinkedIn is absolutely correct. It is simpler, except the complexity is taken up by the human beings to manage the process themselves. Otherwise, you get unsatisfactory results. Okay, now, of course, I wish I could say this is totally simple. Like, suppose Peter has a homestead and it's just him and his family. It's a very known usage pattern. He might be able to have a compost toilet and only have, let's say one problem every 2 years. Maybe when it gets really cold or, really hot or something, something that changes that, right? But of course, in a village, that usage pattern might not be as predictable, right? And there are other things that can happen. So our system, the biochar toilet, is unquestionably going to be more complicated, but what we're doing is we're stuffing the complication into electronics instead of making the human beings deal with it.
Sure, that makes sense. It's a lot more foolproof if you just cook it all, right?
Well, we've not proven that, but we hope so, right? We hope so. I mean, remember, one thing that this project is modular that we haven't addressed is right now what's going to happen is water vapor and volatile gases, which smell bad, are going to go down that pipe, and they got to go somewhere, right?
Isn't that, you just put it on a chimney and then the birds have to worry about it and that's it?
Well, no, I was hoping that we send it to a catalytic converter that actually reduces the volatiles to their constituent nitrogen and carbon materials and carbon dioxide materials. And I believe that is chemically possible, but that process is, I'd like to treat that as a different project than this project, because it's a different problem. Intellectually, the stuff you have to know to do it is different.
But are those compounds simply offensive to the nose, or are they actually environmentally hazardous? Like, is there a good reason to catalyze them, or is it just so you don't smell them?
They're not dangerous. They are only offensive to the nose.
So it does create, so the problem with this system is that because it's a low oxygen environment, you can get carbon monoxide and nitrous oxide developed in the system. It's like when you have like a car engine, you burn lean or you burn heavy, like you basically get like an incomplete combustion inside the products of the because we're basically like in an oxygen-free environment when we do the pyrolysis, it becomes an incomplete combustion, and so the gases themselves are actually a combination of syngas, and those can be noxious and toxic in concentration.
That's correct. I should have mentioned that.
Would it be considered a lean combustion or a rich combustion?
It'd be like lean combustion.
One of the two.
So you have
Because
an excess of oxygen, or
no, it's because of a lack of oxygen.
Yeah.
So it'd be a rich combustion.
Well,
because you have a lot of fuel and not a lot of oxygen.
Correct. Because we actually so the process we're doing, because we thermally we have a sealed chamber, and we're only letting gas escape when we've got a pressure differential. So we're only letting gas escape from the system, and so what's left is basically a kind of like a partial vacuum. Because when we seal it and we let it cool down a little bit between the thermal cycles, we're basically removing all the oxygen in the air, or as much oxygen as we can in the air, and we're not letting more oxygen into the system as it heats up. And all the volatiles that boil off, we're also going to be escaping through the same pressure differential.
well, okay. So let's take a step back here. Okay, if you setting aside the nature of this material, if you take a piece of wood like a log and you stick it in an oven and bake it, and you don't let oxygen come into the system, that is how you make charcoal. Okay, that produces carbon monoxide, which is dangerous, which is also called syngas, syngas. Okay, and the reason for that is some of the material in the wood, which is a carbohydrate, there might be a few hydrocarbons which are different, but the cellulose itself is a carbohydrate. Some of it will leave the chamber in the form of gaseous carbon monoxide. Okay. Now, if you burn it in the presence of oxygen, the carbon monoxide will almost always combine with oxygen to produce carbon dioxide and water vapor if there are hydrocarbons in the material. So I said that wrong. It should probably be thought of as burning rich because there is insufficient oxygen to produce it. Okay, now, I'm not sure it's quantitatively true of fecal matter, but qualitatively it is also true. It must be the case that a certain amount of it will produce a small amount of carbon monoxide, which is, of course, deadly in sufficient concentration.
Sure, that's deadly in your home, but is it environmentally hazardous?
No, not once it gets out the chimney, it's not.
Right. So is there a good reason to try to catalyze it versus just using a chimney?
Yes.
I was going to say maybe not, but go ahead, Lawrence.
So let's think about the normal bathroom in a house. How many of your bathrooms in the house are in a closet or in a basement or in a location where it does not have a vent to the outside?
I mean, all of my, like pretty much all plumbing has a chimney, right? They all have, like all drains have a vent.
Not if they work correctly.
Yeah, I mean, most drains do have a vent that goes up to the roof.
They should. But I mean, they're not really designed for that application, though. But I mean, to put it in plain terms, you, in certain cases, you want to be able to. I mean, you want to basically be able to, But I mean, you don't have to have a. I mean, from an environmental standpoint, you'd ideally want to reduce the carbon monoxide. Like, it's not as bad as like a car, for example, but it is a same kind of air quality hazard that you don't want to contribute to the total amount of carbon dioxide in the atmosphere. So from a health and safety standpoint and from an environmental standpoint, you'd want to go run it through a catalyst to reduce it to carbon monoxide and stable nitrogen oxide compounds.
Is that anywhere, like what's the scale compared to like a cattle farm?
I mean,
tiny.
Yeah.
Tiny.
But if you take like every person in America and you put one of these toilets in their house, then it becomes an issue. So one cow doesn't tip the balance, but a herd of them maybe can. So.
Sure. It'd be interesting to understand the, the effort versus the return. If you had every person with one of these toilets and you catalyzed the gases or you didn't, would it equal 50 cattle farms or one cattle farm or all the cattle farms across the world? It'd be interesting just to know the scale of things.
Yeah.
Well, I think as a forced order approximation, you can use the fact that the average human bowel movement is 128 grams and it's, 75% water. So the amount of carbon we're talking about is tiny. Okay, now there's probably enough carbon in it if you turned it all into carbon monoxide to kill you, but it's tiny compared to the amount of carbon monoxide produced by, say, burning a liter of gasoline, right?
Sure,
so
everyone drives electric cars now anyway, so we don't really worry about gasoline, right?
True. Eventually, we will obtain that state. So I have to admit, Joe, I think intellectually you're right. The reason that I want to do chemical processing is maybe a misguided intellectual desire to do what Buckminster Fuller said, which is just to keep every pollutant in its place. And also the following social reason. Okay, people hate things that smell bad. If our toilet smells bad, even from the outside on the pipe, it's going to decrease the number of people who are willing to use it. Okay, even if it's not actually dangerous. As Lawrence correctly points out, the nice thing about sewage is it takes it away from your house very quickly. It doesn't keep it from smelling. It just smells in a different place, right? So it's possible that I'm letting that sentiment cloud my judgment, because one of the reasons compost toilets are not successful is many people, and maybe I'm one of them, but, I think we can all imagine people who are like, if the compost toilet smells bad twice a year, they're going to want to get rid of it. Right? Like the people are just very intolerant of that. Okay. Now, people could say, well, it's a small price to pay for the reduced cost and the benefits of a compost toilet. And there are many people, at least in America, who would say, I don't care. I'm not going to use a compost toilet unless you can promise me it will never smell bad.
Sure, that makes sense.
But I think you're right, and it's just something that we haven't addressed yet, and that is you probably do need a gas ventilation system, whether we call that a chimney or a vent pipe or something. We're probably not going to like have a bag house where it all gets compressed into a cylinder of noxious gas number 4 for you to use. But
presumably, even if you catalyzed it, you probably wouldn't want it to stay in the room with you, right? Like you'd still
correct. Yeah, correct. It's you still want it to leave. Plus, remember, it's going to have an enormous amount of water vapor in it. Okay. And so as it cools, that water vapor will turn to water as soon as it's sort of not in the system anymore. And so you've got to have some kind of a separation system. Now, the hardware that Hardhik and I bought, does that in the sense that it has a valve, it opens the valve, and when it's no longer under pressure, it cools instantly and condenses in that chrome-plated thing that he called a condenser. That thing's actually called a condenser. But then you've got to do something with the condensate.
So here's just a side question. Like usually when I think about any sort of heat transfer system or any thermal problem, the most efficient answer is almost every single time a heat pump. So is there a reason, like is a heat pump not capable? Because anytime you create a lot of heat from electricity and then you have to vent that water vapor or fumes or anything, you're taking your air-conditioned air and you're pumping it outside and drawing in unconditioned air through the leaks in your home in order to then be re-air conditioned again. So if you can make it a closed system, is it feasible to draw heat energy out of the surrounding air to put into this system to cause your biochar reaction? Or is that too much energy, or what's the deal?
Well, okay, so that's a good point. You could use that as a heat source, but we are using this system as a mass transport mechanism. We're literally transporting the water in the sample away from the sample for the purpose of drying it. It doesn't matter if you do that.
Absolutely, but you're putting energy in from an induction system, not from a heat transfer from the environment.
Right.
Usually that's like 3 times as efficient as just, a resistive heater or an induction heater.
True, but the advantage of Lawrence's idea, and the kitty litter thing was not my idea, is that it gives you the surface area which is in contact with the sample. Now, to do that with a heat pump, you'd have to build like a tube heat exchanger, and the sample would have to be in contact with the heat exchanger, which might work, but then you'd really have to clean it, fairly often, I would think.
Sure. I mean, it depends. I mean, it's not going to transfer heat as effectively, like very similar to what Lawrence was saying about the induction versus a resistive external heater where you have to conduct the heat through the vessel, like whatever pressure chamber you're trying to conduct heat through it versus the heat basically being generated inside of the sample. You have the same problem in that sense, but you're just moving heat rather than, burning energy to create heat. So I don't know. I mean, maybe it's not a good trade-off. I don't know. In general, heat pumps are far more efficient than other sources of electric heat because you're not creating heat, you're simply moving it.
Yes. Well, let me just make it more complicated, okay? So you could try to recover energy from the steam that's being removed, right? Okay, but that would be an additional complexity as well. So all of these things are possible, but my motto is always do the simplest thing that can work, right? And I encourage this team to focus on solving the problem of doing the heating inside a sealed pressure vessel where we can do the water transport and accomplish the charring. Okay. The other things are optimizations that we can add later.
Yeah. So one of the biggest efficiency gains we could gain is by using a heat exchanger for the catalytic converter portion of it. Because what happens with the catalytic converter is most of the ones that we were looking at require a higher temperature to be able to activate the catalyst. And so those would probably be ideal for like a thermal capture or a way of, or maybe like a environmental like heat pump or something that would basically like do that. The problem with the heat pump in particular is because heat pumps are primarily more efficient because they can move heat around more efficiently because they're using I'm going to butcher it, but basically it's a liquid transfer of
Sure. It's a refrigerant.
I'm sure Joe knows that.
Yeah.
We need not lecture him on that subject.
But yeah, I mean, imagine your toilet air conditioning your house. That'd be pretty sweet.
Well,
like, do they have heat pumps that can get that temperature? Because we're looking at like 500 degrees C or F here. It's pretty hot.
Yeah, indeed. I mean, there are lots of different refrigerants that are attuned to different temperature ranges, right? And you can use pure propane as a refrigerant. It's actually a very effective refrigerant. So it just depends on the goals of the system.
I mean, there may be a place for like, so right now we don't have a way of like handling like gas management except by using instead of using a pump, we're using the thermal gradient to act as a thermal pump. But like if we were to pump in a hot gas into the chamber, that could be useful, but I think this would be one of those things where it'd be nice to have somebody who could like do the physics analysis on it to see whether or not like it actually has the gains that we're proposing, because it's almost all like a physics equation problem of mass and heat transfer, given different materials and given different media.
I don't have a question, but I don't know if Lawrence can display the slide where it was highlighting like more probably volunteers or contributors for the project.
well, there's a lot that could be discussed here. Are there any questions which are of a completely different nature, questions from someone who hasn't asked a question yet?
Yeah, I didn't like make it giant, but yeah. So we've like Robert's the Invention coach. I'm I guess taking over the project lead, or at least the phase 2 portion of it. Hardhik did the phase 1, and I think I consulted on that as well. And Peter was primarily being on phase 2.
Okay, thank you.
Okay, well, I'd like to thank our speakers and remind everyone that next month on June 13th, Saturday, if you're in Austin, we're having the Public Invention Con 2026, where this team will be doing a live demo. We'll also have a bunch of other very interesting speakers, including people from Engineers Without Borders and Kids OR.